want to try to find an equation for the current in terms of the variables in the problem, like the speed of the charges, the charge of each charge, and the density of the charges, and so on. So this is a situation what exists at time zero, before the charges cross this area. All of the charges on the left side, and they're moving with a velocity v, and they have an amount of charge of each charge is q. After a certain amount of time delta t, all the charges now occupy this volume after time delta t. The first question we want to ask is, what is the distance that the charges have moved during that time delta t? What is the length, this length? The charges now occupy this volume. So what is the length of this volume? The charges move with a speed v, and they move for an amount of time delta t, then the length is just v times delta t. Now, what is the volume then of this shape? And in this part of the problem, we're trying to find the current, assuming that the charges are going perpendicular. They're moving, the velocity is perpendicular to the area. We're going to see how this changes when the charges go at some angle later on, but for now we're assuming that the charges are going perpendicular. So this volume is just a simple rectangular volume, and the volume is just the area times the length. So you get this for the volume. This is the volume of this region. So now let's see how much charge delta q, the total charge that crossed the surface during the time delta t. But I want to write this in terms of something called small n. Small n is the number of charges per unit volume. So now the question is, what do you need to multiply small n by in order to get the total charge that crossed the surface during the time delta t? Of course, you have to multiply. If you multiply the number of charges per unit volume times the volume, that gives you the total number of charges, but we didn't ask for the number of charges, we asked for the actual amount of charge. So then you just have to multiply by q, which is the charge of a single particle. So this then gives you the total amount of charge that crossed the surface during a time delta t. Now the volume that the charges occupy, we already calculated this. So we can just substitute the volume now as AV delta t. And this then gives us a hint at how we're going to find an expression for the current. Before we do that, let's just identify NQ times V, just define these three things. We'll call it J. And J is the current density, and we'll define it, and we'll talk about it a bit more later on. In terms of J, you can write the amount of charge that crossed the surface during a time delta t as JA delta t, and J is given by this product of three quantities. So what is the average current then during this amount of time? Well, average current is delta Q divided by delta t. So when you divide delta Q by delta t, the thing that's left is J times A. So the average current through the surface is just J times A, where J is this quantity. Called the current density because it's the current divided by the area. You have the current I divided by the area, you get J. So J is the current density, it's the current per unit area. Let's look at the dependence of current in general on small n. So small n, we said it's the number of charges per unit volume. So imagine you have two different cases. This case you have N1, and here you have N2. And N2 obviously is bigger than N1. This is what it would look like intuitively. The small n, when it's bigger, a bigger value, then you have more charges in the same amount of volume. So the charges are more dense. So this is the kind of image you should imagine when you have a large n. This is the kind of image you should have when you have a smaller n. And you can see then why the current depends on small n, because if you wait for the same amount of time, the charges are moving all with the same velocity, and they have the same charge, each one of them, but because there are so many more charges per unit volume, in this case, then the current will be bigger. So this shows intuitively why the current depends on small n. Also, the current depends on the charge of each charge. That should be clear, but let's just take these two examples. In both cases, they have the same n. You see here you have three charges, here you have 5 charges, here you have 5 charges. So the charges here and here are exactly the same density. But the only difference here, I represented the amount of charge of a single charge represented by the size of the charge. So here it's a larger size, that means it's a larger value, and here it's smaller. So the speed is the same in both cases. So you can see then why is the current bigger in this case? Because the charge of each charge is larger. If you wait for the same amount of time delta t, more charge would have passed through the surface during that amount of time because each one of the charges has a larger value here than it does here. And the last thing is how the current depends on V. Why would the current be greater if the speed of the charges is larger? Imagine that if you take a stopwatch and you start the stopwatch when the charges start to go through this area, and then you stop the stopwatch. In the same amount of time, delta t, the number of charges that go through the area will be much larger when their speed is larger. Because they're moving faster, so many more charges will go through this area in exactly the same amount of time. And in these two cases, small n is the same and q is the same. The only thing now is that v is different. So you can kind of intuitively see then why the current depends on the speed of the charges. The units of current are amperes, so coulomb per second is an ampere.